The last topic in this chapter is on linear transformations. Linear transformations. Matrix multiplication by A. When you multiply matrix, whenever you multiply a vector x by A, what happens is AX is always a combination of columns, and all vectors go into the column space. Why? Because AX is a combination of columns of A. So matrix multiplication of A, matrix specifies matrix multiplication of A, matrix multiplication by A means null space goes into origin. All vectors go into column space since AX is, since A times X is a combination of columns. Okay, and remember A is M by N and X is N by N. X is N by N, is an n-dimensional vector. X is an n-dimensional vector. So what happens when you stretch? So how is stretching specified by a matrix? So maybe I give you a definition first. For scalars C and D, for scalars C and D, for scalars C and D and vectors X and Y, matrix multiplication satisfies A into Cx plus dy, which is equal to C times A times X plus D times A times Y. So every transformation that meets this requirement, is called a linear transformation. And all linear transformations can be represented by matrices. So all linear transformations can be represented by the matrices. So this is what we want to do. We want to specify stretching, rotation, reflection, projection. How do we represent these transformations through a matrix? So let's start with the first one, stretching. So in stretching, if you have vectors in x, y plane, so this is some vector x, y. This is a new vector c times x, y. Okay, this is some x-axis, this is some y-axis. So we say a c times x, y is actually some matrix A which we want to find. So A operates on the vector xy, A operates on this vector xy, and we get this new vector c times xy. So I can write A times xy as cx cy, which is equal to, when you multiply a scalar by a vector, so every entry of the vector or the matrix is multiplied by the scalar. So this I can write as C0 x, right, plus, from first chapter, plus 0 C y, which is equal to C0 0 C x y, which is equal to c times I into x y. So ci is the matrix. So this represents stretching. So if c is positive, the vector is stretched in the same direction. If the c is negative, this is stretched in the opposite direction. Okay. So entire space expands or contracts. Expands or contracts. Okay, good. Second one is rotation. And rotation specifically by 90 degrees. Rotation by 90 degrees. So rotation by 90 degrees is, again, you have this xy plane. You have this vector over here, and this vector is, so this is exactly the length is the same. So length is not changed. So the length is the same. This angle is 90 degrees. This is still the origin. This point, maybe I write it like this, x, y, so it's kind of a list thing. So if this intercept is x, this intercept is y, and this is not simply y. And if this angle is theta, if this angle is theta, this angle is obviously 90 minus theta. So if this is x, this is y, what is this intercept and what is this intercept? How do we find out? So this one would be, this one, if this is theta, this point is x, so x is basically cosine theta, and y is basically sine theta, right? So if this is x component, y component, this is, and if this vector is of length 1, this is x cosine, this is cosine theta, x is cosine theta, y is sine theta. Obviously, if the rotation means length is preserved, so length is not changed. Okay, so if this is cosine theta, so here cosine, this one is cosine of 90 minus theta. So cosine of 90 minus theta is cosine 90 cosine theta plus 90 plus sine theta. So this is actually minus sine theta which is simply minus y. And obviously this one is sine 90 cosine theta. So this point is actually sine 90 cosine theta. So this is cosine theta. So this is cosine theta, or this is x. So actually what happens is, so the resultant vector is x and minus y, x and minus y, or minus y and x. So this is cosine theta, this is sine theta, this is cosine of 90. So what is cosine of 90 minus theta? So cosine of 90 minus theta is cosine 90 cosine theta plus sine 90 sine theta. So this is sine theta. So this is sine theta. So sine theta is minus y. This is minus y, and this is x. So x and minus y, or minus y and x. Yes, sorry. So So this one is x component, which is minus y. This is xy component, which is x. So the matrix A times xy. So this vector xy, is transformed into this vector, and this vector is minus y and x. Okay, because this component is minus y, and this component, the vertical component, is x, or this is minus y x. This I can write as, so again I can write this as A times xy equals minus y times x, which is equal to 0 1 x plus minus 1 0 y, or this I can write as 0 minus 1 1 0 x y. This is a rotation matrix, rotates entire space around origin by 90 degrees. Okay. Third matrix is reflection, or third is projection. So third is projection. So projection onto the x-axis. So projection onto x-axis. So projection onto x-axis is, again, I have x and y. So this is also x and y. This is x. So x and y, I have this vector. This vector is again x, y, and I project onto the x-axis. When I project onto the x-axis, this point is x. So this point is x and 0. This point is x and 0. So x 0 is the answer when I multiply vector x and y by a, or a times x y equals x 0, which is equal to 1 0 x plus 0 0 y, which is equal to 1 0 0 0 x y. So this matrix projects onto projects the entire space, into a lower dimensional subspace, into a lower dimensional subspace. Okay. And the fourth one is reflection. So assume again I have x and y, and this is a 45 degrees line. This is a 45 degrees line. 45 degree line. This is 0. So, and this is, so this point is some xy. So this point is x. This point is y. The mirror, the image of this one is somewhere over here, which is so this one and this one. So this point is x, and this point is y. So this point is y comma x. Okay, so a times x y equals y times x, which is equal to 1 0 1 0 1 x plus 1 0 y, which is equal to 0 1 1 0 x and y. So this matrix transforms every matrix, every vector into its image on the opposite side of the mirror, Okay, so we'll come back to these four transformations in a little while. Let me give you the procedure for computing the matrix of linear transformation. So the procedure for computing the matrix that represents linear transformation is, so the procedure is like this. Assume this is some linear transformation that goes from Rn to Rm with respect to basis V as basis V1 up to Vn, and W as basis W1 up to Wn. Okay, so we compute T times Vj, which is alpha 1j W1 plus alpha nj Wj, and this represents the jth column. So this is the jth column, and this is done for, so compute this for j equals 1 to n. So this is the linear transformation. This is some linear transformation. We want to find the matrix that represents this one. So then form the matrix. W1, Wn, TV1, TVN. So form this matrix and get its reduced row echelon form. And what is that reduced row echelon form? That reduced row echelon form is like this. You have identity on this side and you have some matrix A on this side, and this A represents T transformation with respect to bases of V and W, where V and W are the vector spaces. Mathematically, this is also X belongs to some vector space, or T times X is simply T times J equals 1 to N X J Vj. This is writing X as the spanning set. So this is writing X as the set of depending on the basis of V, which is equal to J is equal to 1 to N X J into T of V J, which is equal to J is equal to 1 to N X J, but T of Vj can be written in terms of W. So this can be written as K equals 1 to M alpha Kj W K. This is exactly this term over here. This is exactly this term over here. So alpha Kj, so this becomes K, everything becomes alpha Kj, and this is alpha Nj up to W M. I'm sorry. This is Wm. This is Wm. This is alpha 1j W1 up to alpha Nj Wn. Yes, this is all right. Because we have n components in W, so this is alpha Nj Wn. So this is alpha Mj. So sorry, this should be M, not N, because these are only M vectors. So this should be M JWN. So alpha 1 to alpha M JWN. Alpha 1 to alpha M WN. Okay. And or this can be written as, I can interchange these two sums. So this becomes K is equal to 1 to M. J is equal to 1 to N. This is X J alpha K J, and this is W K. Actually, don't use the square bracket, doesn't make sense. You need to use parentheses here and parentheses here too. So these are the weights. These are the bases. These are the weights that represent Tx in the new basis. Okay. Let me do an example for you. So let me do an example. So let's say T vector space V, which is in R2, goes to W, which is in R3. Okay. And I am given T of x1, x2. T1 of x1, x2 is simply x1 minus x2, and then x1 and x2 as is. So the first component is simply the difference of the two components, and the others are as is. Suppose V has these bases 1 1 because it's R2, so 1 1 and minus 1 1, and W equals 1 0 1 1 0 1 0 1 1 0 1 1 and 1 1 0 1 1 0. So let's find A. Find A. So the first part is find A, the matrix for standard basis. For standard basis. Standard basis simply implies columns uh, of an identity matrix. Columns of identity matrix, which implies, meaning for V, they will be 1, 0, 0, 1, and for W, these will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. So the matrix, we form the matrix. So matrix is W1, W2, W3, T of V1, T of V2, which is equal to W1, W2, W3 is already identity. So when this is identity, when this is equal to identity, this implies this one is the matrix of transformation. Matrix of transformation. It's the matrix of transformation, which is A. So this one is T of V1 means T of V1 simply means these are the differences. The first two components are the differences and the others are as is. So when you have this one, it's 1, 0 here, it's 0, 1 here. This one is 1 minus 0, which is 1. This is 0 minus 1, which is minus 1. So this is the matrix A. This is already identity, and this is the matrix A of transformation. Okay. Second part, standard basis for V, standard basis for V. So whenever the bases are standard for W, so the matrix of transformation is actually represented by TB1 and TB2. So standard basis for V and given basis for W. Given basis for W. So this means standard basis, given basis for W means, so standard basis for V means we have this one as is 1, 1, 0, minus 1, 0, 1, and given basis for W means we have these three vectors 1, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, and then we have 1, 1, 0. Then we have 1, 1, 0. So if I want to do reduced row echelon form, I'll do minus row 1 plus row 3. If I do that, I'll get 1, 0, 1, 1 minus 1, 0, 1, 1, 1, 0, minus 1 plus 1 is 0. This is 1. Minus 1, 0 is minus 1. Minus 1, 0 is minus 1. Plus 1 is plus 2. Then I do minus row 2 plus row 3, minus row 2 plus row 3. If I do that, I have 1, 0, 1, 1 minus 1, 0, 1, 1, 1, 0. Minus 1 is 0. Minus 1 is minus 2. Minus 1 is minus 2. And 2 over here. Then what I do is I say row 3 divided by minus 2, I will get 1, 0, 1, 1 minus 1, 0, 1, 1, 1, 0, 0, 0, 1, and then this is 1, this is minus 1. And finally, I want to get rid of this one and this one, so I get an identity on this side. So I say minus row 3 plus row 2, and I do minus row 3 plus row 1, either order is fine. So I have 0, 0, 1, 1 minus 1. This is 0. So 0, 0, minus 1 plus is 0. Minus 1 plus 1 is 0. Minus 1 plus 1 is 0. Plus 1 over here. Then 1, 0, 1, 0. Minus 1 plus 1 is 0. And then I have minus 1 plus 1 is 0. Minus plus 1 minus 1 is 0. So this is identity. And this is my matrix A of transformation with respect to these bases. And so if T1, so if T of V1 is alpha 1 W1 plus alpha 2 W2 plus alpha 3 W3, and TV2 is beta 1 W1 plus beta 2 W2 plus beta 3 W3. So these represent alpha i's, these represent beta i's. Okay. Third part, given V and standard for W. Standard basis for a given basis for V and standard basis for W. So obviously if there are standard basis for W, we already have an identity here, 1 0 0 0 1 0 0 0 1. Okay, and the basis for V1 is 1 0 0 1. So 1 0 0 1 becomes standard base for this one. So it's 1 1 and minus 1 minus 1, 1 1 minus 1 1. So this is 1 1 minus 1 1, and this one is the difference of these two. So this is 0 and this is minus 2. So since this is identity, this is the required A. So whenever you have the standard basis as for W where you're transforming, so T of Vi represents the matrix A. And finally, the last option is given V and W. So given basis for V and W, given basis for V and W. So given basis for V and W, we have, so given basis for V and W, this matrix is as is, 0 minus 2, 1 minus 1, 1 1, and given basis for W was 1 0 1 0 1 1, 1 0 1 0 1 1, 1 0 1 0 1 1, and then last one was 1 1 0, 1 1 1 0. Again, if we do transformation, minus R1 plus R3, we'll get 1 0 1 0 minus 2, we'll get 0 1 1 1 minus 1, minus 1 plus 1 0, 1 minus 1 1, and minus 1 and 2 plus 1 3. Okay, and then I do minus R2 plus R3. If I do that, I'll get 1 0 1 0 minus 2, 0 1 1 1 minus 1 0, minus R2 plus R3. This is 0, this is 2, this is 0, this is 4. And if I divide, and now if I divide by 4, so if I do R2 divided by 2, then I'll get 1 and 2 here, 1 and 2 over here. And then I want to get rid of this was minus 2, sorry, minus 1 minus, sorry. This was, I'm sorry. This was minus 2. This was minus 2. Minus 1 is minus 2. Sorry. Minus 1 is minus 2. And this one was 4. So if I do R3, I'm sorry, R3 divided by minus 2, I'll get 1 over here, and I'll get minus 2 over here. And then I do two operations again to get rid of this one and this one. So I say minus R3 plus R1, and I do minus R3 plus R2. If I do that, I'll get 0, 0, 1, 0, minus 2. And over here, I'll get 0, 1, 0. So minus 1, 0, 1 as is. 2 minus 1 is 1. Then I get 1, 0, 0, minus 1, 1, 0, 0 as is. And then 2 minus 2 is 0. So this is identity, and this represents A for this particular transformation. Okay, good. Let me give you another example. Let's do another example. Another example is T of x, y, z transforms into x plus y and y minus z. So the sum of first two elements and the difference of the second and the third element. Let's say V is represented by this basis 1, 0, 1, 0, 1, 1, and 1, 1, 1. And W is represented by, so V is in R3 and W is in R2, 1, 2, and minus 1, 1. Okay, so what we want to do is we want to find A for given basis for V and W. So find A for given basis for V and W. So again, I form the matrix. I have 1, 2 here. I have minus 1, 1 here. This is x plus y, so 1 plus 0 is 1. And this is 0 minus 1, minus 1. 0 plus 1 is 1. And 0 plus 1 is this, 1 minus 1 is 0. This is 1 plus 1 is 2. 1 minus 1 is 0. And then I do minus 2 R1 plus R2. When I do that, I'll get 1 minus 1, 1, 1, 2. Minus 2 plus 2 is 0. 2 plus 1 is 3. Minus 2 minus 1 is minus 3. Minus 2 minus 4. And then I do R2 by 3. If I do that, this will become 1. This will become minus 1. This will become minus 2 by 3. This will become minus 2 by 3. And this will become minus 4 by 3. This will become minus 4 by 3. Okay, then I want to get rid of this one. So I say R2 plus R1. If I do that, I'll get 0, 1 here. I'll get minus 1 here. I'll get minus 2 by 3 here. I'll get minus 4 by 3 here. This will be 1. This will be 0. 1 minus 1 is 0. Minus 1 plus 1 is 0. 1 minus 2 by 3 is 1 by 3. And 2 minus 4 by 3 is minus 2 by 3. Oh, sorry. 2 minus 4 by 3 is 6 minus 4, so it's plus 2 by 3. So it's plus 2 by 3. So 0, 1, minus 1, minus 2 by 3, and minus 4 by 3. So this is A. This is A. Again, T. So this implies T of V1 is actually alpha 1 W1 plus alpha 2 W2. T of V2 is beta 1 W1 plus beta 2 W2, and T of V3 is gamma 1 W1 plus gamma 2 W2. This represents alpha i's, this represents beta i's, and this represents gamma i's. Okay, so let me see what we are trying to do. If x is 163, this implies T of x is, so 6 plus 1 is 7 and 6 minus 3 is 3. So this is 6 plus 1, or 1 plus 6 probably. It's 1 plus 6, and this is 6 minus 3. So x plus y and y minus z. Okay, and if x is alpha 1 v1 plus alpha, or maybe I do some delta here, delta 1 v1 plus delta 2 v2 plus delta 3 v3, and delta is this vector minus 3 2 4. So just check. So this implies minus 3 into v1, and v1 was 101 plus 2 times v2 was 011 and v3 4 times v3 was 111. So if v3 was 111, this implies we get minus 3 plus 4, which is 1, 0 here, 2 plus 4 is 6, minus 3 plus 2 is minus 1 plus 4, minus 1 plus 4 is 3. So this x is the same as this x. So these are the weights. So these are coefficients in coefficients that multiply the basis vector. Coefficients that multiply basis vectors in V. Okay. So how do you find the coefficients of, how do you find coefficients of basis vectors in W? So the easiest one is, so those coefficients, let's call them lambda. So lambda times lambda, or sorry, lambda is actually a times, we'll find coefficients of basis vectors into, say, lambda i's. So lambda is actually a times delta. And what is A? A is this vector matrix 0, 1 by 3, 2 by 3, 0, 1 by 3, 2 by 3, and this one is minus 1, minus 2 by 3, minus 4 by 3, minus 1, minus 2 by 3, minus 4 by 3. This is multiplied by minus 3 to 4, and we get what? We get 2 by 3 plus 8 by 3 is 10 by 3, and here we get 3, which is 9 by 3. 9 by 3 minus 9 minus 4 is 5. 5 minus 16 is minus 11. Minus 11 by 3. So or T times x. should be equal to first coefficients 10 over 3 times W1, 10 over 3 W1 minus 11 over 3 W2, which is equal to 10 over 3. W1 is 1 and 2. W1 is 1 and 2 minus 11 over 3. W2 is minus 1, 1. And this is equal to 10 by 3 plus 11, 21 by 3, which is 7. This is 20 by 3 minus 11, which is 9 by 3. 9 by 3 is 3, which is exactly the same. This one is exactly the same as this one. So different bases get the same result. This is what we were trying to see. Okay, the matrix that transforms the basis, that transforms from one vector space to another vector space, can also transform the coefficients. Okay, so let's go back and apply this same technique to, again, rotation, projection, and reflection. So rotation through theta, rotation through theta. Okay, same vector, but now we will have standard basis for. So standard basis for V and W, and everything is in 2 dimensional, so we can easily draw a picture. So if I draw this picture, it's not a straight line. So this is X, this is Y, this is some vector. This one vector was 1 and 0. This vector somewhere over here is 0, 1. This angle is theta. This angle is also theta. Okay, same, looks the same. So this component, so this, since this vector is 1, so if I project onto this one, so this one is cosine of theta. Cosine of theta, let me call this C, and the y component, so the y component, this is the x component is cosine of theta, and the y component here is going to be sine of theta. Sine of theta, which we call as S. Same argument here, so this will be actually minus sine of theta, and this would be plus cosine of theta. So my matrix would be actually 1, 0, 0, 1, standard basis, and then I'll have cosine theta, sine theta. So again, when I project this one, this will be cosine and sine, cosine on this one and sine on the y-axis. This is all right, and this is the opposite one. Here I'll have minus sine theta, and I'll have cosine theta. This is the projection. This is the matrix. We call this Q of theta. If theta is equal to 90, we go back to the one that we calculated in the beginning of this lecture. So what is Q of minus theta? So Q of minus theta reverses rotation. It reverses rotation. And when it reverses rotation, this simply means replace theta by minus theta. So this is cosine of minus theta. This is sine of minus theta. This is minus sine of minus theta. This is plus cosine of minus theta. So cosine is even, sine is odd. So we get cosine theta, sine theta, minus sine theta, and this is cosine theta, which is actually the inverse of Q of theta. So this is actually Q theta inverse. Okay, and if I want to do Q theta, and then I want to do Q theta square, so Q theta square is simply Q of theta into Q of theta, and you can go home and check. This is actually going to be equal to cosine of 2 theta, sine of 2 theta minus sine of 2 theta, and this is cosine of 2 theta. So it's simply matrix multiplication in trigonometry. And if you have theta plus phi, so q rotation by theta and then by phi, or phi and then theta, this will become cosine of theta plus phi, sine of theta plus phi. I don't want to calculate this. You can go home. You can at home, at your own time, you can actually calculate and see if these are actually correct. Theta plus phi, and this is actually q of theta plus phi. So in general, A and B are linear transformations, linear transformations from V to W and U to V respectively. Then if U belongs to U, this implies BU belongs to V and ABU belongs to W. So this is the linear transformation from U to W. This is the linear transformation from U to W. Okay. And if you want to rotate by 90 degrees, followed by reflection around x-axis, this implies we'll get, so rotate first. So rotate first means 0 minus 1, 0 minus 1, 1, 0. So this is rotation by 90. Rotate by 90. This is reflect across x-axis, and this will be 1, 0, 0, minus 1, which is simply equal to first row, because we are multiplying, because of this one, and second row would be minus 1, 0. Okay, what about projection? So after rotation through theta, and then projection P onto a line at theta degrees. So again, if I draw this picture, this is and then I have this one. I have this line. This line is theta here. This one is 90 minus theta. Again, I have this vector. This vector is 1, 0. This vector over here is 0, 1. And I project this vector. I project this vector onto this line. So this is 90 degrees. And I project this vector onto this line. This is 90 degrees. So this point, and I have this point over here. This line is in cosine theta sine theta direction. This line is in cosine theta sine theta direction. This intercept is cosine theta. So this point is actually cosine square theta cosine theta sine theta. And similarly, this intercept, maybe I write it in, maybe I do it in red. So this intercept is sine theta. So this point is sine theta cosine theta, and this one is sine square theta. Okay, so my matrix is, so my projection matrix, so my projection matrix P, because I'm still using standard basis, this is cosine square theta cosine theta sine theta. This is sine theta cosine theta, and this is sine square theta. So no inverse exists. Once you project you onto a lower dimensional plane, and points on orthogonal lines, this is for orthogonal, this is not independent, orthogonal lines project onto the origin, and obviously lie in null space of P. Okay, and points on theta line are projected onto themselves, which implies projecting twice is same as projecting once, that is P square equals P. So projection matrix equals its own square. Okay, good. So the last one, or maybe the second last one, is reflection. So reflection, and I'm going to find it through another method. So projection P or rotation Q through theta. Okay, so reflection, I'm going to find it another way. So suppose this is the line through theta. This is the origin. This is the vector, and this is its image. Maybe the image is maybe this is the image. So if this is the image, yeah, probably looks like right. So this is vector x. This is x projection. This is x perp. This is the perpendicular, and similarly, this is minus x perp, and this is x reflection. Okay, so this is the point. This is the theta line. This is the angle theta is making in. So we can write x reflection is actually x projection minus x perp, x perpendicular. But what is x perpendicular? This is x projection minus x perpendicular is x minus x projection, or this is equal to x minus x projection, which is equal to 2 times x projection minus x. This I can write as 2p times x minus I times x, or this is equal to, or this implies h times x is 2p minus I times x, or reflection h is simply 2, this is projection is 2 cosine square theta, 2 cosine square theta minus 1, 2 sine theta cosine theta, maybe I write it below this one, or h equals 2 times cosine square theta, 2 times sine theta cosine theta, 2 times sine theta cosine theta, 2 times sine square theta, and then when we subtract minus 1 0 0 1, this is equal to 2 cosine square theta minus 1, 2 sine theta cosine theta, this is actually cosine 2 theta, 2 sine theta cosine theta, this is 2 sine square theta minus 1. And if you put theta is equal to 45, so if you put theta, if theta is equal to 45, you get the same result as the one we calculated, in the beginning of this lecture, as the one we calculated in the beginning of this lecture, Okay. And if you reflect twice, if you reflect twice, you come back to the original position. You come back to the original position. This implies h squared is equal to I, or h equals hi, or h, or reflection is its own inverse. Good. The last one is shear. And this is like this. You have a deck of cards here. This is a deck of cards, and you lift this one up. Let's say this is x1 axis and this one is x2 axis. So, and this is some vector x. So if you lift this one up, this implies this figure is going to be like this. This is going to be like this. So this is going to be up. It's going to go up, and like this. Okay, so this portion is this is slope k. If this slope is k, this is actually k times x1. This is x1, right? this is k times x1, this is x2, and we say T of x. So so this is the vertical shear. So T times x is simply T of x1, x2, or x and y, and this is simply equal to, so x1 is x1, x2 is x2 plus k times x1, which I can write as 1, 0, k1, x1, x2. And similarly, for horizontal shear, you can go home and calculate. So for the horizontal shear, this will be this thing. So this is x1, this is x2. Maybe I draw it on this side, doesn't look nice. So this is x2, this is x1, x2, and if I do a horizontal shear, which means I push over here, so this is going to be like this. And you can go home and check. This is going to be A is, so this is A is given by 1K01. So this is all we want to do in chapter 2. Just to recap, matrix depends on choice of its basis. Goal is to make a matrix diagonal. So we want to diagonalize a matrix. In chapter 5, we will see A becomes S inverse AS. A undergoes this transformation. So a single transformation is represented by different matrices via different bases accounted for by matrix S. So chapter 5 and onwards, the goal is to diagonalize a matrix. Chapter 4 is on determinants, and I think you can do it yourself. And chapter 3 is how to orthogonalize the basis vectors. Because if you look at coordinate geometry, you assume that the coordinate axis is orthogonal, because this eases your computations, and this is what we want to do in chapter 3, how to orthogonalize set of vectors, whether these are the basis vectors or any vectors, and there we'll see the two subspaces in Rn and two subspaces in Rm are orthogonal to each other, and they are called orthogonal complements. Again, if you have any question, you can email me, or we can discuss it on Mondays and Wednesdays. That's all. Thank you very much.